Okay, good morning, everybody. Welcome to our second seminar of the semester. This morning, we had the honor of having Professor Ivan Arraut. He's a physicist by training. He's a professor at the University of San Joseph in Macau, China. He obtained his PhD in the School of Science at Osaka University in Japan. So he spent a good amount of time there in Japan. Before that, he got both master and BS degrees in Colombia. So again, he's a hardcore physicist, but he has tried to use the concept of physics in business applications. So that will be an interesting talk this morning. The topic of the presentation is, the title of the presentation is Implementation of the Tools of Physics in the Scenarios Involving Economics and Finance. So I'm going to be recording this presentation. As I told one of you, to make sure that you receive credit for this seminar, you may want to capture the screen during the presentation, maybe a couple of times, so you can make that part of the handout for the seminar. Okay, the handout that you need to submit later this semester. Also, what I'm going to do, I'm going to mute myself and I'm going to turn my camera off, so in order not to disrupt the speaker. Okay, so let me do that. So, Ivan, the floor is yours.
Okay, so I start, no?
Yes, please, go ahead.
Okay. So, my name is Ivan Arraut. I am from Colombia, working here, University of San Joseph, Friday midnight. It's a pleasure to be here talking to you. I will mention I am a multidisciplinary researcher. I am trained in physics and engineering, but somehow I do research in different areas, and one of the areas I do is finance and economics, basically implementing tools of physics, and that's the purpose of my talk today. This talk is based on previous publications. One of them is in Physica A, which is a Elsevier journal. You have the reference here. The other is Europhysics Letter, EPL is an IOP journal, and the final one is Mathematics, is a MDPI journal. And there are other in process. I will be talking about that in a moment. Let me see. Change the slides. Okay. First of all, one of the most popular formulations in physics, and not only in physics, in all the areas of the science, actually, because it's very general, is the Hamiltonian formulation. The Hamiltonian formulation is equivalent to the Lagrangian formulation, as I will explain in a moment. The difference is the type of problems you are confronting. For example, the Hamiltonian formulation, I will explain here, is the favorite to be used in problems involving atomic physics. Why? Because in atomic physics, or in physics where there are no relativistic effects, where you are not taking into account that the particles move at speeds near to the speed of light, for example, the Hamiltonian formulation is good enough. Hamiltonian itself is not a relativistic invariant, because the eigenvalues are the energy. And if you study special relativity, for example, the energy by itself is not a relativistic invariant. It's part of the quadrivector, which contains energy and momentum. However, if we are going to confront, this part is the physics, not the motivation of using Hamiltonian formulation. If we are going to study problems involving high energy physics, for example, the favorite formulation is the Lagrangian formulation. Then there is always this question. People always ask, when do you use Hamiltonian? Why do you use Lagrangian? Well, Hamiltonian when there are no relativistic effects. I mean, when the particles don't move to speeds near to the speed of light. And the Lagrangian formulation is when the opposite occurs. When the particles move near to the speed of light, it's easier to handle, the problems are easier to handle if we use the Lagrangian formulation. Why? Because the Lagrangian is a relativistic invariant. So, I mean, let me clarify this point. Both formulations contain the same information, okay? The difference is that if we use, for example, the Hamiltonian formulation in the problems which are the particles accelerators study, for example, in the CERN, in Fermilab in Chicago, that they accelerate particles, those particles move to speeds close to the speed of light. I mean, they perceive relativistic effects. Then if you use the Hamiltonian formulation, you have to use Lorentz transformations for transform the Hamiltonian. It's very complicated. It will become a mess, the problem. With the Lagrangian, you don't have this problem. So with the Lagrangian, you use the Lagrangian, it's invariant. You don't have to worry about converting it to anything. Sorry. So this formulation is emerged from where? I am sure that if you, well, I am not sure if you study that, because normally mechanical physics, for example, when people study mechanical physics, they don't, not necessarily you see Lagrangian or Hamiltonian formulation, but even the Newtonian laws, for example, can be formulated in a Hamiltonian formulation, a Lagrangian formulation, but that's not so useful in such a case, no? This becomes more useful when you go to quantum mechanics and these kind of things, okay? So now let's see how these formulations emerged. It was, well, the first guy who implemented or to explain the let's say these formulations at the quantum level was the genius Richard Feynman. He was the type of physicist whose lectures were so brilliant that they are recorded in some books. Actually, the Feynman lectures in physics are some of the most famous books you can find in any library. Well, he explained quantum mechanics in a unique way. For example, when he wanted to find the wave function of an electron, he imagined, for example, you put a box in a room. Let's assume that this is a box and the particle is free to move inside the box. Then he assumed, okay, since I don't know the trajectory of the particle, I will imagine that the particle can be everywhere. And I will assume all those possibilities. When you assume all those possibilities, you obtain the wave function. So he was the first guy who really interpreted in a very nice way quantum mechanics, quantum field theory, and other issues. Double slit experiment is one of the cases where this Feynman interpretation is very useful. I think you're familiar with the famous Young interference experiment, where you throw light, basically, and there are some interference patterns when the light crosses the double slit, for example, particularly when the wavelength is longer than the separation of the slits. Well, in quantum mechanics, when you throw particles one by one, for example, you throw electrons one by one, they create an impact pattern in the screen. And that impact pattern follows exactly the same pattern of interference as the light or anything. This gave us the wave-particle duality, the de Broglie wavelength, and many other issues which are interesting inside the scenario of quantum mechanics. And in this case, also the Feynman interpretation of all the possible trajectories, for example, a particle traveling from the initial point toward the slit can move freely everywhere. But once cross the slit, it has only two options, the first slit or the second slit. So in quantum mechanics, the interpretation is that the particle crosses the slit, the two slits simultaneously, and that's why it creates that interference pattern. That's the interpretation, the universally accepted interpretation, and when you do that, you obtain the correct results. That's the strangest thing of quantum mechanics. Now, let's change the issue. We were in pure physics, no? We were explaining the motivation, why the Lagrangian formulation is nice, why the Hamiltonian formulation is nice. Both formulations are equivalent here. For example, this transformation you see in the slides is called Legendre transformation. It's for converting from Hamiltonian to Lagrangian and vice versa. So basically, when you have a Hamiltonian of a system, you can find the Lagrangian and vice versa. So basically, for formulations contain the same information. Now that we explained the motivations for using one or the other formulation, let's go to finance and see how these formulations can be used for explaining results which are already known. No? For example, the Black-Scholes equation is a famous equation which was the first serious equation able to predict the behavior of the stock market. It was derived, of course, by one guy called Black, the family name Black, and Scholes. No, you can find the references in this book of Bacchue. It's from Cambridge University Press, but also there is a paper for Black-Scholes where the derivation of the equation appears. But it comes out that equation can be expressed in a Hamiltonian form. And why is so convenient to express in a Hamiltonian form in this way, how it appears in the screen? Because then we can find the Hamiltonian operator as it appears here. In this Hamiltonian of Black-Scholes, sigma is the volatility. X is a quantity, is a variable which depends on the price of the stock. R is the interest rate, which is fixed by the banks. So basically, there are ways to convert the Black-Scholes equation to a Hamiltonian form. And what's the advantage? Because we know how to solve Hamiltonians. We know how to find eigenvalues. This at the end, it becomes an eigenvalue problem. So you can find the eigenvalues, the eigenvectors, and you can solve the problem very easy. Besides that, when you have the Hamiltonian, you don't need to know. You can solve the dynamic of the system without solving the equations. Let's say you don't have to solve the equations exactly for understanding sometimes the dynamical behavior of the system. And I will explain that in a moment. Then how Black-Scholes derived the equation? First, they did something very smart. They created a portfolio. Well, these are economic issues, which there's a portfolio, you have a quantity in the, an asset, let's say, in the stock market, and you find a derivative of that asset, something which is correlated, some quantity such that the price of that quantity is correlated to the price of the initial asset. Then you can cancel the random fluctuations of both quantities, okay, in similar way as we do in physics with renormalization, for example. And then if you do that, you cancel the random fluctuations, then you can find an equation able to make a exact prediction of the prices of the stock. And that's what Black-Scholes did. Of course, you don't have to understand the details of this, but you will realize that this equation, which is here below, is exactly the same equation I showed you before. This equation is exactly the same here. The difference is that here we defined a Hamiltonian and we did a conversion of variable. No, you can see that the derivatives here appears with respect to S. S is the price of the stock, and S is equal to exponential of X. If you replace this here, you obtain the operator, which you see here. And something important to remark here is that the Black-Scholes equation made the predictions of options. Options are contracts done between two parties, holder and writer. And the prices of those options, they have their own market, but the prices depends on the prices of the stock. That's why you see a wave function here, which is the price of the option as a function of the price of the stock. These are the Black-Scholes solutions. I will not mention all the details. I will just mention quickly that C is the price of a call option, and PU is the price of a put option. Call option is when you have the right to sell in future. You make a contract today, and you agree to sell that contract in future at a predetermined price. These are details which I don't find relevant to explain in deep detail, because the key point of the talk is that even if you know the solutions, sometimes the solutions are not necessary for explaining the dynamic of the system. That's the advantage of the Hamiltonian formulation. Look at all these parameters. Look at all the parameters. Price of the options, price of the stock, time to maturity, strike price, volatility, and interest rate. Basically, the key parameters here, which define the dynamic of the system, are the volatility and the interest rate. In the Hamiltonian formulation, we don't need the details of the solutions for understanding the dynamic of the system. And that's a huge advantage. And that formulation is brought from physics, obviously. Then this is the importance of bringing that formulation to the scenario of the stock market. There is another equation, more complex. While the Black-Scholes equation assumes that the interest rate is constant, there is another equation which considers the interest rate as a stochastic variable also, in the same way as the price of the stock. This is the Merton-Garman equation, and the Merton-Garman equation also can be expressed in a Hamiltonian way for obtaining the Merton-Garman Hamiltonian. Merton, this is one of the original papers deriving the equation, but the Hamiltonian form can be found in the book of Bakier, which I shared, the reference I shared initially. This Hamiltonian looks quite complicated, but there are ways to analyze in a simplified way the dynamic of the system, concentrated in the potential of the Hamiltonian, give you the conditions of equilibrium and give you some clues about the dynamic of the system, the symmetries and dynamic of the system without solving the equations. So something important which emerged in the stock market in both Merton-Garman and Black-Scholes Hamiltonians is a ground state, vacuum. In physics, we deal with vacuums the whole time. The vacuum has energy, etc. But one consistent way, something which is universally accepted, is that the Hamiltonian annihilates the vacuum. For example, the Hamiltonian operator applied to the ground state gives you a null value. So there is a condition in the stock market equivalent to a vacuum, and that condition is called martingale state. The martingale condition occurs in the stock market when all the participants of the market, they have the same amount of information. Think for a moment, what's the advantage? Why some people can make money in the market and why others cannot? The difference is information. Who has more information can earn more. Who has less information has a huge disadvantage. So if for any reason everybody in the market has the same amount of information, then that market is in equilibrium. Nobody wins, nobody loses. And that condition is called martingale state. And if we express the equations in the Hamiltonian form, it comes out that the Hamiltonian annihilates that state. So that state behaves as a vacuum. So that's quite interesting. In the book of Peskin and Schroeder is the best book in introduction to quantum field theory. They explain the concept of ground state. Now, something which is important to mention in both Black-Scholes and Merton-Garman Hamiltonians, and in many other systems, biological systems, chains of production, anything you wish, you can use Hamiltonian formulation. You can use Lagrangian formulation. These are variational principles which are general. But there is something which is very important, identifying the free parameters of the system. What are the free parameters of which govern the dynamic of a system? Why? Because depending on the value of the free parameters, the ground state of the equilibrium condition will change. Sometimes your ground state condition is unique, as it happens in this plot. Look at this plot, which is an example with a Gibbs potential. When the temperature is bigger than a critical, there is a single ground state. When the temperature is smaller than a critical temperature, the system develops two ground states, and spontaneously the symmetry is broken. Some symmetry is broken. In this case, magnetization, the symmetry related to magnetization, which is related to the rotation of the system. But this means, in general terms, that in any system, when the free parameters change, the structure of the vacuum changes, and that changes the dynamic of the system. And this occurs in finance, in economy, in biology, everywhere. So let's assume a magnetization, for example. Let's go to the example of a magnet, ferromagnetism, which is the most popular, one of the most popular examples you can see in your career. What is ferromagnetism? Is when all the magnets or all the spins of the system align in a single direction. Think for a moment, when the temperature is high, the spins of the magnets align randomly. So, and the Hamiltonian describing this system, is rotational invariant. And when the magnets are oriented randomly, this system, the ground state or the vacuum state, is rotational invariant also. However, when you decrease the temperature and you put some magnet, you put some magnetic fields, the magnets start to orient in one direction. What does occur? Your Hamiltonian describing the dynamic of the system still is rotational invariant, but your ground state is not. For example, if I go inside this circle, for example, look at the circles. If I go to inside this circle, which point the arrows below, this area is not rotational invariant. If I rotate around it, I will perceive something different because all the magnets are oriented in one direction. If the magnets were randomly oriented, that system will be rotational invariant. The ground state will be rotational invariant. In conclusion, in ferromagnets, when all the spins are oriented in one direction, we call this condition a spontaneous symmetry breaking. A spontaneous symmetry breaking means my Hamiltonian still respect all the symmetries, but my ground state violates some symmetries. In this case, rotational invariant. When my ground state violates some symmetries, it means that the operator represented that symmetry doesn't annihilate the ground state. That's why in the right-hand side in this slide, you see this operator operating over the vacuum, it cannot annihilate the vacuum. Okay, so this is the condition for spontaneous symmetry breaking. I will explain in a moment how to apply this in the market and in the market equilibrium and so on. So in the stock market, we did some research. We did some research before, and we realized that the symmetries in the Merton-Garman equation, the symmetries under changes of prices are spontaneously broken, and the symmetries under changes of volatility are also spontaneously broken. This brings some interesting results. It gave us a compromise between volatility and prices of the stock, something which can be tested experimentally. Actually, we can collect the data and see if this expression is really true or not, or under which condition this expression is valid, this condition of the left, bottom left in your screen, on your screen. In the Black-Scholes equation, the Black-Scholes Hamiltonian, the structure is simpler. Only the symmetry under changes of prices was spontaneously broken. And the expressions emerging in such a case are simpler, not as interesting as in the case of Merton-Garman, let's say. So this is the famous, for you to understand what happened when the symmetry of a system is spontaneously broken, this is the famous Mexican hat, the most famous potential which you will find when you study spontaneous symmetry breaking. Look at the ground state, the vacuum is not in the center, no? The vacuum is the ring you see in the bottom. So when the system reaches this condition, the system has to select any one of these points in the ring below as the vacuum state. Once the system select one ground state, maybe because of external magnetic field or external induction, something, then all the system has to align in that direction. In the case of ferromagnet, what happened? Once the system select the direction of magnetization, all the magnets align in that direction. That's equivalent to select one of these ground states. Interestingly, all those ground states are orthogonal to each other, and they represent different Hilbert spaces if we talk mathematically. Now let's go to the market equilibrium. Now we changed the scenario. We were in the stock market. Now let's go to the ordinary market equilibrium, supply and demand curves in economy. The demand curve has negative slope because, of course, when the prices are high, less and less people buy, which is the yellow curve you see here. And the green curve is the supplier curve. Suppliers, because the suppliers only get motivation to produce any product if the product is expensive enough to be sold, no? Because I mean they need some motivation. Think for a moment, if something becomes expensive, then many people will start to produce that in order to sell it. It's a motivation. Oh, let's produce this because it's expensive. Then we can sell it in a good price. Okay, that's the green line. The intersection of these two curves gives you the market equilibrium. The market equilibrium means the agreement of the prices between the suppliers and the customers. It marks the price which you see in the supermarkets or everywhere, basically. Sometimes there are shifts, etc., but normally there is the equilibrium condition is always reached. So I think I have like 14 minutes in my understanding, so I will try to be a little faster. These are the examples. These are the standard.
Yeah, 15 minutes. So
15 minutes.
Yeah,
okay.
No problem.
These are the same examples. These are examples of shift in the market. No? It happens for different reasons, for intervention of governments, or because the gas become expensive, or I mean there are many reasons for the fluctuations of the prices of a product. No? The right-hand side is the consumer surplus and producer surplus. These are economic terms which can be studied from this book. It's not difficult to understand. The consumer surplus, you can see, is the difference of prices between what the equilibrium price minus what the maximal price, which, or vice versa, the maximal price which the consumers are willing to pay minus the equilibrium price. The producer surplus is some kind of mirror image of that. But what I want to mention here is that even this market equilibrium can be formulated in a Hamiltonian form. But before mentioning that, I must say that when there is no intersection, for example, in this case, there is no agreement in the prices between suppliers and customers, the suppliers say, okay, nobody wants to pay the price of this, I will not produce anything. So there is zero production in this case. It means that you will not see this in the supermarket, that product will disappear. Now, in the Hamiltonian, there are ways to formulate the market equilibrium. For example, the demand. If you analyze a little bit, the demand, we describe it linearly, but it's not necessarily linearly. We express here, look at the equations here on the right-hand side. We express these expressions are linear between quantity and price. And the market equilibrium is when the quantities are equal and the prices are equal also. But here, there is no loss of generality if there is quadratic dependence or so. So if you analyze a little bit, a Hamiltonian describing the demand behaves as the Hamiltonian of a harmonic oscillator. And the Hamiltonian describing the supply behave as the Hamiltonian of an accelerated particle. And of course, you can still play in the same way as we played before. You can find the market equilibrium first, agreement in the prices. If both both parties agree in the price, you obtain this expression. And the total equilibrium is what not only the prices are the same, but also the quantities, no? The demand and supply are the same. And that is reached under these conditions. This is the equilibrium for quantity. This is the equilibrium for price. It can be derived. This is only a plot of the Hamiltonians. The yellow one is the harmonic oscillator. The other one is the accelerated particle. They have some intersections. And it can be demonstrated that supply and demand is some kind of zero-sum game from the perspective of game theory, which I will not explain in detail here because there is no space for that. And now what happens in some scenarios, there are cases where there are corporations which are merged. For example, sometimes the governments decide to either privatize some sector or acquire the sector. When there is fusion between organizations, it's very useful to formulate these supply and demand systems as a single, let's say these two separate systems as a single system. And it's possible to do that if we formulate it in this way, with this Hamiltonian. The Hamiltonian is quadratic in the prices, but quartic in the quantities. And this Hamiltonian behaves exactly as a system where the symmetry can get broken spontaneously. Look at the parameters. The parameters are A and B. A depends on the difference of the Hamiltonians, the supply and demand, which I explained before. And the potential will be this. If you find the ground state of this potential, you will find something interesting. You will find this solution. When A is larger than 0, this is a trivial result, is where the suppliers decide not to produce anything. There is 0 quantity. There is no agreement. There is a single vacuum. There is a single condition equilibrium, which is empty. Only when A is negative, and this happens when the Hamiltonian of the demand is larger than the Hamiltonian of the supply, then in this condition, the symmetry is broken and a non-trivial result emerges. In this case, what happened? A bunch of customers, it's like they orient in the same direction, but orient in the same direction in this is like a magnet. A bunch of people say, I agree to buy this product at this price. Many people agree to buy a product at some price, and that breaks the symmetry of the system spontaneously. It's just an analogy. So, and this, well, this results is a paper which is, well, actually it's already submitted, but I say process of submission here, but just for mentioning it. So, as you can see, before going to another area, as you can see, the variationals methods, which are based on Hamiltonian and Lagrangian, are very useful. And as you can see, in the sense of humans being, breaking the symmetry, you have to make the interpretation. For example, why is the symmetry here? The symmetry is with respect to changes in prices or with respect to changes in quantity or so. You have to specify. And the breaking the symmetry in this case is related to collective decisions. And these collective decisions are related also, can be used for predicting why some president is elected. Presidential elections, for example, in presidential elections, we can use the Hamiltonian formulation and find symmetry breaking patterns which explain why a bunch of people decided to vote suddenly for one candidate or the other. These kind of formulations can explain the propagation of a pandemic, for example, why a pandemic suddenly appears. That's a paper which I also produced with some colleagues, which I didn't mention here because I wanted to focus in finance and not deviate to the medical sector. But I mean, you will find that there are plenty of applications in this direction. Now, if we go to the game theory, decision trees is something you see in standard courses of probability. I am sure that some of you, if you have seen the courses of probability, you have dealt with decision trees. And it's one of the simplest way to formulate probabilities, conditional probabilities, etc. In this case, in this scenario, there are other tools different to the Lagrangian and Hamiltonian that can be used. And that's another paper which is in process. For example, when you have nodes, for example, you know A, B, D, Z, each node, of course, represents one event, no? So, and each line represents decisions, okay? Decisions taken by the entity A, the entity B, entity D, etc. But how to deal with multiple decisions? It seldom happens that the books explain that part. And there is a powerful tool dealing with that, which is the quantum Jambaster equation. Quantum Jambaster equations are triangular relations, actually, like this, which appear in physics, mathematics, and in other areas of science, and can be used for study triangular relations between nodes. For example, here each R matrix is a node, and each line represents a decision. Okay, and these are equivalent decisions. For example, these triangles are equivalent. So it's a way to find equivalent decisions, and each line, internal line, is a multiplicity of decisions taken simultaneously. For example, when you're driving a car and you drink a coffee simultaneously, that can be put as two lines here, red line, yellow line, and so on and so on. So how many lines? It depends on the problem which you analyze. I just wanted to mention this as a final motivation, that it's also possible to implement this kind of tools in analyzing social problems. So I will conclude here after explaining the quantum Jambaster motivation. My conclusion is that the tools of physics are very useful for analyzing practical problems. You always wonder, oh no, physics is only for, basically physics is what we do is we take mathematics and we try to model the nature. But mathematics is a general language. So the same equations can model many systems, and you can find that, and those analogies also. For example, when you study heat transfer, sometimes you make analogies with circuits, no? In electricity, in electronics. Let's say you can make heat transfer, and you can model the heat transfer between systems as parallel circuits or so. So, I mean, why you can do that? Because mathematics is a universal language, and there are ways to find the same equation in multiple areas. This happens the whole time. And not so many people realize, because they just focus in a single area, no? But if you start to see multiple areas, you will find, oh, this is the same equation I saw in this area, and so on and so on. And sometimes you get ideas from one area, you can map to the other, and vice versa. So it's very useful to go to multiple disciplines sometimes. I must mention that the variational principle, Hamiltonian Lagrangian, they contain the same information. This variational principle is the most useful way to analyze the dynamic of a system without solving involved equations. Importantly, you don't have to solve the equations for understanding the dynamic of a system. It's a huge advantage. And finally, different values of the free parameter of the system involve different behaviors of the dynamic of the system, particularly the ground state. Basically, the ground state behavior changes, as I mentioned, in the case of the ferromagnetism, and in the case of the Gibbs potential, which I showed before, and in the Mexican hat. With this, it remains only 2 minutes, but I will conclude here with the talk. I am open to any question or comment you want to do. Thank you.
Good. Thank you for such an interesting presentation. Let me ask the students if they have any specific questions. I have a question, but let me see if any students have any specific questions about the presentation, about any of the topics.
Yeah, I have a quick question. Can the Hamiltonian be used to predict changes in the market, or is it just used to describe what is happening in the market currently?
If I understand your question, you are asking if the Hamiltonian can predict changes in the market, or what is happening in the market right now.
Yes, can it be used to predict changes?
Well, the Hamiltonian itself is the generator of the let's put it this way, is the generator of the translation in time, no? So by itself, it can help you to make predictions, no? But beyond that, what is happening right now, well, if you extrapolate, let's say, because normally in finance, when you analyze finance, you go from the present to the past. No? So if you want to know, if you want to understand why is happening, what is happening right now, you apply time reversal, no? And you can more or less understand what happened before, for such that you can explain what is happening right now. I don't know if this is what you mean, but basically the Hamiltonian itself describes the dynamic of the system and help you to analyze the evolution of this system. Yeah.
Thank you.
Yeah, kind of a follow-up question. Has anybody, including yourself, have done any kind of validation of that approach? I mean, where you take this Hamiltonian approach and somehow you look at historical data, compare it to present data, and then based on that, being able to validate,
Well,
your
yes,
assumption.
some work has been done, not yet delivered, but yes, it has been done. Particularly, I explained before that when you analyze for example, in the Merton-Garman case, when you analyze the symmetry breaking patterns, we found a compromise between price and volatility. This can be tested with the data. It could be, of course, in the case of the Black-Scholes, for example, which is the simplest equation, the Black-Scholes has been tested several times, of course, and is an equation used by many investors actually for predicting the prices of the options. Okay, the fair price of an option, the fair price of an option, because it's a little bit different to the price which appear in the charts because there is an arrangement. The fair price is when nobody wins, nobody loses. And that equation is validated. All what you are doing in that case is you're transforming the same equation to another language. Okay, I mean, you don't change the equation. Let's say the Black-Scholes equation and the Merton-Garman equation already there. And somebody else have tested it with data and so on. And what we do here is just write in another language, which simplify the analysis of the dynamic of the system. And some interesting constraints emerge, which of course can be also tested in charts. But yeah, your question is quite interesting, and there is a lot of work to do in this direction, of course, because as you know, the stock market is one of the most difficult things to predict. No?
Yeah, and there's always a element of irrational behavior, right? Even though
exactly.
even though most economists claim that it's kind of rational, but what happened in 2009, 2010 proved that it was not very rational. So,
yeah, it was not rational. And actually, something interesting about the stock market is that information is not preserved. Let's say in quantum systems, for example, ordinary quantum systems, that we have something called unitarity, which is the conservation of information, but the stock market is non-unitary. It doesn't preserve information. And so it makes the predictability a little bit more difficult than the usual, precisely because of that characteristic. That's why it can be proved that the Hamiltonians, mathematically, that means that the Hamiltonians in the stock market are non-Hermitian, while in quantum mechanics, the Hamiltonians are Hermitian. That's one fundamental difference, which I forgot to mention, but it deserves to be mentioned now. Yeah.
Now, I don't know too much about this, but when you look at this formulation that you have here, I mean, it looks like it's deterministic, right?
Yes.
But I guess many people that want to predict the stock market, for instance, may need to consider the stochastic behavior, right?
Exactly.
So how do you take that into account?
That's a good question, and that's the brilliancy of Black-Scholes was that precisely because it's unpredictable and there are random fluctuations. What Black-Scholes did was to create a portfolio. This pie you see here is a portfolio. This phi is an asset, and this minus the derivative of this is another asset which is related to the first one. They are related. And they put this minus sign by purpose because they want to cancel the fluctuations, the stochastic fluctuations of this variable with the stochastic fluctuations of the second variable, which is correlated. And that's how they could make this, let's call it predictive in some way equation. I mean, that was a huge, actually that was an overpriced in economy, I think. The Black-Scholes equation gave an overpriced in economy because they were the first guys who could really formulate something deterministic, let's call it that way. The stock market, of course, there are some issues. For example, they assume that the time is continuous. The time is not continuous. It's really, you know, that it's finite. In the periods of evaluation are finite. That's just an idealization. And there are other simplifications. For example, the volatility, they assume to be constant, but the volatility is sigma. The sigma here is the volatility, which is related to a standard deviation, but it's not a standard deviation. It's called volatility. It's constant in the Black-Scholes equation. After Merton Garman came and they use a stochastic variable for modeling the volatility, but I think the Black-Scholes is good enough for doing root predictions, very primitive predictions, or at least some estimation of what will happen with the prices of the option in a market. I repeat something which I said before. One thing is the price of an option, and one thing is the price of the stock. But the price of an option depends on the stock. The option is a contract done. For example, if I do an agreement with someone and I sign a contract, I pay for that contract, I am buying an option, a call option. That option gives me the right to, let's put the right to sell some asset at a future time for a predetermined price, by a determined price, no matter what happens. And in future, I decide if I execute the option or not. And depending on that, I will win or lose. But let's say the contracts of options are different. The price of an option is different to the price of a stock. That's one of the confusions which many people have when they deal with these equations, because you see, for example, this psi and this S. S is the price of the stock, psi is the price of options, but they are completely different. But related, no? They are different but related.
Good.
I
Yeah. So any other questions from the students at this point? I have another question, but let me see if the students have any questions at this point. So I have another question. How feasible will be to use real-time data from the market to feed that information into the formulation to be able to predict or to come up with the best decisions in the short term, right? So if I'm a stockbroker, for instance, right, and I know what the market is doing, right, I have access to all these data from what's his name, Bloomberg, right? He provides all that data. You have to pay a fortune for that. But if you can get access to that data, is it feasible though to take all that data in real time, do some analysis, and make a decision to be able to make a decision, a good decision to make money the same day or the next day, right?
Yeah, I think this, for example, this, if you collect the data and you compare with this model, what you will do is to obtain the parameters, the values of the parameters day by day or during the periods you consider, and see if the approximation, this is an ideal approximation, of course, see how good is your approximation and how much is deviated from the real data. And then, for example, if you want to do machine learning, you need to introduce a model, no? Initial model. This could be a model, for example, for doing machine learning. You input it and the system will learn only the parameters, sigma and R, for example. The system will learn the parameters and train and so on, these kind of things. Of course, but since this is ideal, there might be deviations with respect to between the ideal case and the real case. And those corrections from the real case will appear as in this Hamiltonian. You can see the R. After this term, there might be some correction terms, which depending on the data, you can perceive if they is necessary to introduce or not. But initially, in the very root sense, sigma and R can be learned with real-time data. Yeah, that's what you would do if you use this formulation in such a case.
To become rich. So, yeah. All right. Well, let's thank the speaker for his nice presentation this morning. Let's do this. Thank you for your presentation this morning. Thank you for taking time. I know that is it's probably 1:10 in the morning in Macau right now, right? So it's
correct.
So you probably want to go to bed now. Okay, well, thank you again for the nice presentation, and we'll see you later. All right.
Okay, see you. No problem. Thanks. Okay. Thanks for the invitation. Bye.
All right. Bye. Thank you.
Thank you. I should finish the call. Yeah.
Yeah, let me stop the recording.